Hello, everybody. Welcome to Professor Goswami's fourth lecture, BNG.
Okay. Thank you, Rama. Thank you, Rama, again, and welcome everybody to the fourth lecture. Today, I'm going to talk about the force, motion, and tropics. Now, why do we talk about force, motion in the tropics? Because it turns out that uh, most of the uh, most of the circulation, the quasi-stationary circulation in the tropics are essentially forced by some forcing and results in stationary motion as a result of forcing and dissipation. Let me give you a few examples. Let us look at our first the monsoon circulation. I'm going to discuss this in some detail later on, but our monsoon is associated with these low-level cross-equatorial flow and cyclonic vorticity in the continental region, producing a monsoon trough here. And then in the upper level, we have this anticyclone and strong producing what is known as easterly zeta. So this circulation where does this circulation come from? How is it forced? So it essentially, it looks like that it is very strongly associated with the heating associated with the rainfall. So here I'm plotting the rainfall pattern during summer and the circulation on the top of this. You can see that the circulation is very closely linked with the heat, the precipitation maximum. The precipitation, wherever there is heavy precipitation, it produces a heat source, and this heat source produces low pressure area, and this heat source then produces convergence of wind towards that low pressure area. And due to the Coriolis force, these winds then turn around and goes. And since this heat source is slightly away from the equator, it produces quasi-geostrophic motion going around it, and it produces the cyclonic vorticity. So it appears qualitatively that this circulation is essentially a result of forcing due to the heating associated with rainfall. And there are many such examples in the tropics. For example, we would like to understand this quantitatively, that can a linear theory tell us, given heating, are we going to expect exactly this kind of circulation? And that is what we are going to do today. So other examples of such circulation in the tropics are response of the atmosphere with, for example, heating associated with El Ninos, or again, so and El Nino and La Nina. So these are the color is SST anomalies associated with an ensemble of El Nino events during December, January, February, and the winds are composite of wind anomalies associated with during all these El Nino events. So these are kind of wind anomalies associated with those SST anomalies of the El Nino events. So this shows that the SST anomalies, the winds are converging towards the warm waters, and it produces response of equatorial response in the form of a vortex this side and that side, and of course there is divergence in between, and in the globally there is a response, and in the Indian Ocean there is warm anomaly, and these winds also attract towards the warm anomaly. So it again appears that this is surface response. So now if I go to response of the winds associated with El Ninos, again the color is the SST, and the winds are at 200 hectopascal. So at the upper atmosphere, the wind response is very clear, very even clearer than at the surface, and there are these divergence in the upper atmosphere. Now in the lower atmosphere, you see that the wind converges to this heating associated produced by the SST anomaly, and then but in the upper atmosphere that the wind then diverges and produces atmospheric response in the form of two vortices, so a twin vortex around the equator. This is a very classical example of a response of atmosphere to heating associated with the convective heating associated with these El Nino events. So qualitatively, that is what we know, but we want to understand that more quantitatively in terms of the structure of the winds. Given this heating, does the atmosphere respond to form these kind of wind anomalies? That is what we will try to address today. Similarly, for the La Nina also, if you take several La Nina events, and you have, of course, the negative anomaly here. At low level, there will be divergence of winds, and the upper level, there will be convergence of winds. That's the opposite. But look at the structure. This is almost opposite structure that we can see in the during the El Nino events, and so therefore, so the La Nina events will represent some sort of a anomalous decrease in heating, and the so in a sort of negative heating, if you can call it. There is nothing like a negative heating, but it is sort of a weakening of the heating and strengthening of the heating, and that is this, in the anomalous sense, is a negative heating here and the positive heating in the other cases. So how do we understand that? To understand that, we have to look at the response of the atmosphere to these heat sources. And to understand that response of the heat sources, we need the equatorial waves. And so before going further into the actually doing the calculation, let me recap some of the things that we discussed in the last class. So some of the properties of the equatorial Rossby waves. So we have these basically, so we have these Rossby waves, westward propagating Rossby waves, the free Kelvin wave, the Rossby, mixed Rossby gravity wave spanning the both eastward and westward propagation, and the inertia gravity waves. One of the things that I want to remind you that the inertia gravity waves, for very long inertia gravity waves, the frequency is nearly zero. That means they are more or less stationary, and this character, this property we might have to will have to actually use at some point of time today. I will just come back to that. So let us try to remember some of the other structures again. So the structure of the function, the amplitude function in the structure of these waves, Rossby and inertia gravity waves are like this. And what I want to note is that, for example, this is something that we discussed. We could not discuss very in detail last lecture, and there was some question about it. Just recall that these for n equal to 1, for example, the V for the meridional winds are proportional to psi 1. That means it is symmetric, antisymmetric about the equator. But U and phi will be symmetric. They are n equal to 2 and n equal to 0. So so for n equal to 1 Rossby wave, V is antisymmetric and U and phi are symmetric. Now, when to find the divergence of this, you have to differentiate in the U to del U, del X, and del V, del Y. So the V has to be differentiated with respect to Y, and when you differentiate V, it will become symmetric. So when differentiate these Hermite functions once, the antisymmetric function will become symmetric. So the divergence associated with the n equal to 1 Rossby wave will be a function of psi 0 and psi 2 that is symmetric about the equator, and that is why similarly the divergence associated with these Ni wave will be, see, V is symmetric, therefore this will be antisymmetric. Divergence will be antisymmetric. It will be proportional to psi 1. On the other hand, for the Kelvin wave, this divergence V is 0, and and U and phi are symmetric, therefore divergence will also be symmetric about the equator. So these are properties that was required to understand these powers of the inertial gravity wave, the mixed Rossby gravity waves to be antisymmetric, and the Rossby waves to be symmetric, and Kelvin wave to be symmetric. And that is what, because these are the variations of the OLR or are associated with the updraft and downdrafts, and that updraft and downdraft are vertical velocities. Vertical velocities are nothing but divergence and convergences, and therefore the divergence and convergence of the structure is related to these vertical velocities in the large scale, and that vertical velocities in the large scale associated with them gives rise to these variations in the OLR. And that is why we can identify them with that. So, okay, some other important points to remember is that the pre-equatorial Kelvin wave is stud propagating, Rossby waves are stud propagating. These are non-dimensional dispersion relation. And for long Rossby waves, the phase velocity of the Rossby, Kelvin wave is non-dimensional 1, but the phase velocity of the Rossby waves is 1/3. Therefore, Rossby waves are about 3 times slower. The gravest Rossby waves are 3 times slower around the equator. And there's another important thing is that k is equal to, for very long waves, very close to the very long waves, close to k is equal to 0, the group velocity and the phase velocity of all these waves, Kelvin and Rossby waves, are equal. So these are a couple of things that we need to remember to interpret some of those results that we are going to discuss today. Before going further, there was another question that someone asked. Actually, Dr. Shankar asked me after the lecture yesterday, the other day, that from the extra tropics we know that the Kelvin waves need a boundary for existence. Now, how then a free Kelvin waves exist in the tropical atmosphere? So this is an interesting question, and I did not explain it clearly the other day. So I just make a explanation here and before moving forward. So this is essentially due to the special nature of the equatorial beta plane, where your equatorial your Fy is just beta y. There is no F0. On the other hand, extratropical beta plane, we have a ambient background mean vorticity, mean Earth's vorticity, or F0. This character of the equatorial beta plane actually makes the Y structure of all the waves evanescent away from the equator on both either side of the equator, both sides of the equator. You remember this P structure, which is e to the power minus y square by 2, and this psi and whatever it is, this function, this exponential function makes it evanescent, sort of decay away from the equator on both sides. That makes it like the equatorial beta plane acts like as a sort of dynamical channel. Even though there is no physical channel, the dynamical channel sort of confines these waves, trap them around the equator, and that is why it makes a Kelvin wave possible at the equator. But same thing is not possible in the extratropic because of this kind of a dynamical channel is not possible, because around the center there will be one side the F will be decreasing, another side the F will be increasing, and this kind of a thing will not happen. So that is, I think, is a sort of important point that needs to remember in general. Okay, with this background, again, recap of the background, let us go to the understand some of the force motion in the atmosphere. So how does the force motion actually gets established in the atmosphere? So we can understand force motion in the atmosphere as a result of a balance between or sort of steady state motion in the atmosphere. Some of these motions are quasi-stationary. This stationary motion can happen only if there is dissipation in the system. If there is no dissipation, the forcing will produce generate perturbation. This perturbation will produce the waves that are allowed. Those waves will propagate out of the forced region, and then if there is no dissipation, they will continue to propagate. There will never be a steady state. Now, if there is a dissipation, then of course the force the waves will decay away from the source region at depending on the rate of dissipation, and the rate of it will dissipate away from, and then the certain distance away from them will become negligible. But that distance will depend on the dissipation rate and the propagation of the waves. So when the rate of dissipation and rate of generation, the forcing will keep on generating these waves, but and then they will propagate out and dissipate. And so when the rate of generation and rate of propagation, rate of generation and rate of dissipation balances, then you will have some sort of a steady state, and that is how we will get a steady state. So how do we study the steady state? We can go back to the same linear equations. Now we need we have discussed those same beta plane equations. So same basic equations here. I have still not made beta plane, but I will make it beta plane. So those linear equations. Now, if I drop the time dependent term, these are the equations for the steady state. Now, for steady state, we need forcing. These are the forcings, and I need this dissipation. Now, dissipation is now here in a very simple way represented, what is known as a relay friction for the winds or the momentum, and what we call Newtonian pulling for the heating or mass circulation. So this Newtonian Newtonian relay friction comes from essentially, the friction is essentially due to the shear of the winds at the surface and the upper levels, and the shear essentially produces instability. That instability produces this diffusion, turbulent diffusion, and therefore, but you can simplify it. So it is essentially at the surface the winds are zero. Therefore, upper level or the low level, the winds are this is the free wind, and therefore it will be eventually proportional to the free wind in some way. So therefore, we can make it a very simple approximation. Everything is rather simplified in this formulation. And here we are assuming that the heat dissipation rate and the momentum dissipation rates are equal, which is not really true in reality, but they are different. But for simplicity and for doing this analysis easily, sort of more tractable way, we are keeping them equal at this point of time. So so we need dissipation and forcing. These are momentum forcing. So in the atmosphere, there may not be much of a momentum forcing, but when you go to ocean, the wind stress will give a momentum forcing. But in the atmosphere, we will have heating. Heating will come from radiation balance and latent heat rating heating that will be realized from the clouds and precipitation. So this will come back to that in a minute. So this equation remains same as our basic linear equations. Now let us look at one idealized case. This was in the I referred to the Matsuno's paper in the last talk, and this is a very classic paper. And in this, he first did these normal modes in the absence of forcing. Then he also had a little bit of discussion on if we have a very periodic forcing, sinusoidal forcing in the east-west direction. In other words, in the east-west direction, forcing is positive, negative, positive. Just like a wave, the forcing has a wave structure in the east-west direction. If that is so, then the analysis becomes very simple, and he did a simple analysis for the force motion, and I'm reproducing some of that here. So in this case, the the forcing can be so now the equations of motion will now you will assume that the forcing has a periodic structure in the space direction. Therefore, you can write the all the variables also as e to the power chi x e to the power ikx x, and therefore you can find the basic set of equations can be now written in this form for the amplitude functions. Now that is similar to our linear unforced case, but with the forcing in place. Forcing is also now decomposed into these ikx functions. So with that, and the boundary conditions remain same, and then you can actually put these equations. Now that we know that in the absence of forcing, there is a whole set of solution, free wave solutions, which are a complete set of solution, and we can assume that the whole force solution will be also a sort of base is a sum of these. We can expand the force solution in terms of these complete set of free solutions, and then find out which are the modes that will be actually have amplitude, and that is the basis for this analysis as we go along. So with that, we can simply write this in a simple way in a matrix form. This equation can be written. The left hand side is written here, and this sigma is a matrix which involves these forcing functions. Okay, so with that we can then we remember that in the absence of forcing, there is a set of Eigen functions which are the basic normal modes, and they can be written in this form, where this omega is the frequency associated with each of these Eigen modes. So with these are kind of free solutions, and then we can use these free solutions to expand the variables chi and as well as the forcing, and these uv pi as well as forcing functions all can be now expanded in terms of these Eigen modes. And if we do that and put them back into these equations, you get a similar set of and this M is a whole set of possible Eigen modes that are there. We can use the use of this this relationship for the free modes. We can use that, and then finally this equation becomes like this, and then you can use the orthogonality relation of these functions are Eigen functions are orthogonal. Therefore, you can use the orthogonality relation, and then by doing that, multiplying both sides by one of these orthogonal functions, and for each mode, I can find out what is the relationship between the amplitude functions, and that is essentially gives me a relationship between the amplitude of each of these modes as a function of this forcing. So if there is a forcing, these B's are from the forcing. So forcing is projection. This is a projection of the forcing of that particular mode, and then this is the frequency of that mode, and this part has a dissipation. Now we know that dissipation has a time scale is several days, and therefore only those waves which are low frequency waves, the high frequency inertial gravity waves and gravity waves will not resonate, and and therefore the dissipation time scale and the frequency of these waves or the modes for which they are similar, and they will only resonate, will give me amplitude for those modes, and that is therefore it is basically going to get response only on the larger scale waves, and this you can find out using these normalization constant from the orthogonality relationship. So now suppose I take a very special case of, say, that the forcing function is just symmetric about equator, symmetric but periodic. Something like this. So it is symmetric about equator. So equator is here, the forcing function is symmetric, but it is periodic in the east-west direction. And then if I go back and try find the solutions, and the solutions will actually look like this. So this is very interesting, and what we see here is that there is around equator. You see these Kelvin wave type of response. The winds are all zonal, and there is elongation to the east, which essentially is due to the higher phase speed of the Kelvin waves, and they propagate a little faster to the east, and therefore their response extends further to the east relative to these responses of equatorial response are essentially due to n equal to 1 Rossby waves, and that is slower, and therefore there is a tilt in the equator towards the east, sort of extension towards the east. And these, you can see that these white is the Rossby waves. Actually, I can go back and actually look at those structural functions. And but if you just see the, you see that the zonal winds in this region are symmetric about each other. So these zonal winds are same here and here. They are symmetric about equator, but meridional winds, if you see, they are antisymmetric about equator, and that is the property of the Rossby waves. And that so therefore the pattern emerges as a result of a response. The projections come into the Kelvin wave one, because this structure is very much like Kelvin wave. Therefore, large responses comes from the Kelvin wave, but the Kelvin wave response is essentially very close to the equator, but away from the equator, response comes from the Rossby wave. And therefore the final response is looks like this. So this is like like this, we can actually develop a sort of linear model can give us a response in a very special case. Now, what we need to do is, in reality, the heat sources are not so periodic in the east-west direction and around the globe. And this is very unusual. This is not possible, but it gives you an indication how the response takes place. Okay. Now let us go to the what is the time? So I'll break here for a minute, and then we'll go. Next we'll go to actually basically a more complicated or more reasonable sort of heat source, where which is localized. Suppose I have a heat source like monsoon. Monsoon heat source is localized, right? There is the rainfall is just confined over a smaller region. And now, given that kind of a heat source, what will be the response? And that requires, can we solve this kind of a process using the using the same linear set of equations? And that is what Gill did some time back, and I think that is what makes this paper a very classic. And he showed that that we can actually solve these for very even very complicated localized heat source, which can be decomposed into a number of symmetric, antisymmetric heat sources. And then for each of these symmetric and antisymmetric heat sources, we can go back and find out solutions, force solution, and then you add up. So you can actually do that, and that you can do even analytically, and that was the beauty of this. So this is something that we'll discuss now. So at this point, let me stop. This is just about half an hour. We can have a few questions, and then I will move on to discuss in detail how this model of Gill's model. Okay. Rama and Anupam, we can have a break.
Sure. Thank you. Professor Rama, you can go ahead and answer the question
Yeah,
first.
so I had a question, BNG, like where did you use your the fact that these wave eigenfunctions are orthogonal to each other?
Oh, Oh, in our in the solution in the last class, I did not highlight it, but they are all orthogonal because they are what you call let me see. You see, the solutions are based on these functions. Now you can see. So if we see the sinusoidal functions are all orthogonal, right? Now these Hermite functions are also are all orthogonal, right? These are based on all orthogonal functions. Therefore, they are in each of them are are orthogonal. So therefore, so if you go both.
I'm asking is like, did you use that fact anywhere for any derivation?
No.
Okay.
It is just a result of our basic solution. The solutions are a set of orthogonal functions, and it is also complete because although I have shown that these equations are solved by assuming that the constant part of the coefficient of v is an integer number. Now that is an assumption, but you can find out by numerical method all the complete solutions, and it turns out that there is no other solutions than these. So this form actually there is a lot of other ways people have shown that all the solutions that we get through that Hermite function relationship, Hermite equation relationship, that are the only solutions that are allowed.
Okay.
See, Rama, see, the thing is, if you have a stable equilibrium situation, dynamical system, and when you perturb, I am Narasimha speaking.
Okay.
You know me, and you all right.
Yeah.
See, the thing is, if you have a stable system, and now if you take perturbation, and there is no dissipation, it is a Hermitian self-adjoint system. Now, if you put appropriate boundary condition, it becomes Hermitian.
Right.
Then whatever he said, the orthonormality and all the things, subject to, again, Professor Goswami mentioned, you need the correct boundary conditions.
Yes.
These are the standard things. Yeah, you know it well. I don't think I should tell you, but that is how it goes.
Okay, no, the reason I was asking all this is that we recently wrote down these things in spherical coordinates. I mean, the full spherical, not beta plane. And we found that they are not self-adjoint, the final equations. But we can talk about that offline.
Okay. I think that will be good. The normal modes and spherical geometry, people had done this, but there are issues about those which I don't remember offhand, but we can discuss this at some point of time.
Yeah. Okay.
Again, there the thing is, if you were to put the equations because of the coupling, when you have rotation, there is problem. But even then, way back, I think in the 1960s, I think it is our Lyndon Bell and the Princeton person, short. They have shown even in the rotating system, if you do not have dissipation, they are Hermitian system. Only question is that since the coefficients have these imaginary terms, how exactly, but that is a separate thing. So the Hermitian system, even for a rotating system, as long as you are in the correct reference frame, you will find that it is a Hermitian system, I think. It is Lyndon Bell and Oestreicher's result in the 1960s, I think.
Thank you.
But again, I do not work in the field, so I do not know. That's why I am asking questions to Professor Goswami rather than
thank you, Dr. Narasimha. I think that is very nice, important comment, and I think these are things that are going to connect the two sides. Okay.
But since ICTS has told that, now I can ask my question. Now, what I asked you last time, you mentioned now about the forcing, etc. But my problem still is that once you have a n equal to 1 rho P wave, how exactly this connection, once you have the heating, between two layers, because it is essentially only along the horizontal direction you have the wave, no vertical structure. So in that sense, about these forcing terms. And so that is my first question. That is, so the thing is that if you take only n equal to 1 Rossby wave,
yes,
where exactly is the vertical structure? Where all this
vertical. Okay, the vertical structure in all this shallow water formulation, there is an assumed vertical structure, and in fact, I am going to talk about that in a minute here.
Okay,
in this,
okay, in that case,
there is
very
an
good. I will wait.
assumed vertical structure.
No,
So,
no, that's a good idea. Okay, you will tell it later. I don't want to preempt. My only other thing there is, the question is that why do you want always that, okay, there will be dissipation. If it is there, there is no problem. But you have forcing, because of that the amplitude grows high. And so the wave probably transports your energy from between equator and pole, what you mentioned. So in that sense, why do you always need the dissipation equal or this thing? Because steady state is only if you take a global structure, isn't it? Or I am missing the point there?
No. I think you are just slightly sort of missed one thing. I should have mentioned it more clearly. So right now I am talking only about the tropical heating, tropical response. Only tropical response. The last time when we talked about the waves transporting energy, that is in a global sense, and the global sense, and that works mostly on the extratropical system where there is waves are transporting. In the tropics, the transport of energy is largely through this mean meridional circulation, the Hadley circulation, and the response within the tropics are due to these waves. So it is within the tropical belt. Right now I'm confining myself. Okay.
Okay. Thank you, Professor.
Okay. Any other question on the
yeah, Professor Goswami, so we can attend to it at the end.
Towards the end. Okay. Then just give me 1 minute. Okay. So as I said, the Gill came up with a very nice simple way of calculating the response of the atmosphere to a given heating, given localized heating, and that is what I'm going to try to discuss now. So this so I'll talk about what are the model approximations and how the model solution for different and then conclusions. So the model is designed to show the response of a tropical atmosphere to diabetic heating. Diabetic heating meaning that non-adiabatic, essentially the radiative or the convective, the associated with the precipitation. So this is where the vertical structure of the heating comes into play, and that is where we have to assume a vertical structure of these in the atmosphere. So basically, the vertical structure of the heating is associated with only radiative forcing. Suppose it is only land surface heating, and that tries to heat the atmosphere. It has to come through the sensible heat flux, and that is essentially confined into the boundary layer only. So the vertical structure of that heating will be decaying from the surface to the top of the boundary layer, and therefore the vertical velocity from the thermodynamic equation, if you see, is very much related to what is the heating. And therefore, if there is no heating, there will not be any vertical velocity, and therefore the depth of the circulation will be determined by the vertical structure of the heating. Now, for convective heating, the heating is maximum at the middle atmosphere, and therefore there is a large vertical structure. There is heating going up all the way to the top of the atmosphere and to the bottom of the atmosphere, but at the maximum at the middle. So therefore, it is a large vertical, and this essentially projects into a first baroclinic mode structure of the atmosphere, and that is what is for most of the studies here. We are assuming that there is an assumed first baroclinic mode vertical structure of the heating, and then then the horizontal structure equations are essentially horizontal structure for that particular vertical assumed vertical structure. And so we are just going to ask this. These are essentially linear theory. Therefore, we are assuming that perturbations are small and within the linear domain, and so it will give us at least the basic structure, but it may not give us the amplitude correctly. So essentially, the expansion of the forcing functions will be in terms of the normal modes of the as well as the of the normal modes of the system. So, so this is the vertical structure we are going to assume. This is something like a cost function, and sort of maximum in the middle, and so on. So this is something that Gill used in that, and sort of makes sense to use it. And this is where that. Rama, you asked me some time back, and what kind of vertical structure we assume. That basically this is what we do, and then we can get an equivalent depth corresponding to that normal mode. Okay, so Salvator equations will be used, and beta plane, etc. Non-dimensional as usual. So this is similar to what we had done in the free modes, but now I am adding the dissipation. Now here I am using a different symbol, but here I am using dissipation, this reflection as epsilon, and this is continuity equation. And this continuity equation, as Professor Narasimha asked the other day, the continuity equation is some sort of an equivalence to, in a very simple way, to the thermodynamic equation. This is sort of in a mass. So the thermodynamic heating and cooling produces mass sources and sink, and so we are going to use these and equivalence of that in this heating term. So it is sort of mass source and sink, which possibly is associated with heating and cooling, and this is dissipation, like Newtonian cooling. So so these equations are very similar, but forcing and dissipation are here. So now how do we solve them? If the heating function is localized, and that is our main issue. So he uses a slightly different length scale, and it doesn't have just a factor of 2. Therefore, in our earlier, I did not have that factor of 2. So therefore, in these Coriolis beta term, there is a factor of 2, 1/2 coming instead of just 1. Otherwise, these equations are exactly same as our equatorial beta plane equations, except for the forcing and dissipation. So with that, we can then expand this. Now let us go to steady state. Now, if we say steady state, we drop the time dependent terms, so the equations become again very similar to those I used earlier for the periodic case. But this third equation now can be written that in the steady state, so the vertical velocity is proportional to heating. So and this is dissipation. So if there is no dissipation, vertical velocity is just proportional to heating. So if there is no heating, there cannot be any vertical velocity. So the vertical structure of the circulation is going to depend on the structure, vertical structure of this heating. And here we have assumed that kind of a structure. So if I now simplify these equations now and get an equation in V, so I need to get an equation in V, or so this is a bit of an algebra you have to go through, and then finally you will get an equation of this type. This looks a little bit complicated, but we can make some simplifications, and that simplification is associated with, because as we know, the most of the dissipation is weak, and therefore, and the scales of these are large. The scales of these heating, horizontal scale of the heating is pretty large. So most of the response is going to be projected into the larger, low frequency, large scale modes, and therefore we can make something called long wave approximation. So our epsilon parameter, that dissipation is small, epsilon 2, epsilon k is much smaller than 1. If that is so, then I can make something called a long approximation and neglect some of the terms, and what we then some of the terms will be can be dropped here based on these. And then when you go back, your basic equations become only the V equations become just the geostrophic balance. The rest of the them, so it essentially is under long wave approximation. This equation becomes simply geostrophic balance, and therefore you simplify this. So this makes a hell of a lot of simplification, interesting simplification, and retains still the main character of these function. So with that, we have now this set of equations. Now this set of equations, now I can solve by some variable transformation, and then this variable transformation is not so you can do it without it, but it gives you helps you in sort of solving them a little easier. So with this now you get instead of P and PU and PU and B. So we have P, Q, and R. P and U are written in terms of Q and R. So the Q and R are related to pressure and geopotential and zonal wind. So the equations becomes instead of U and P. So V remains there. Instead of that, a V equation is a geostrophic balance, and that these two equations are written in Q and R. And so now we can now expand these equations, all these forcing as well as the basic variables in terms of the free solutions, which are in the form of the Hermite polynomials, right? We know that the free solutions are as functions of Hermite polynomials, and therefore we can expand everything in terms of these Hermite polynomials and Hermite polynomials with exponential. This Dn functions. I'm sorry, sometimes I have used size. Here it is D, but please don't get confused. There is only slight changes in the. So once I do that, and by using the properties of these Hermite polynomials, you can actually get the equations for the amplitude functions. So something like this, and these are of course what you call the relationship between them of the orthogonal functions. So then we put them back into the equations and then find out the coefficients of different eigen functions, and then the equation, the coefficient function equation becomes so the partial differential. Now it is like like converting the partial differential equations into a set of ordinary differential equations by expanding them into orthogonal functions, just like we do in the numerical weather prediction models. So here, interestingly, you get a few relationships which are which will give us, given the structure of these forcing functions, some of them will remain, some of them will not remain, depending on which, where the projections of the forcing comes from. So with these relationship, I will not go into great details, but just show you how, given a heating, how they will project into some of these coefficients. So let us now talk about some specific heating functions. Now, instead of let us talk about a symmetric heating function, where the Q is actually is just a function in the x direction. So there must be a function in the x direction, because localized function is now, this is not sinusoidal, but some function in the x direction, and then there is a y function. Y function is in the form of these Hermit polynomials. This is the zero order function, the exponential function, and the antisymmetric. So this function is symmetric about equator, and then there will be another function we'll see where the same x variation together with an opposite function, opposite antisymmetric function in the y direction, and that is y into e to the power minus y square by 4. So this is an antisymmetric heating function. We'll try to find out solutions of those equations for foreseeing of this form, in these two forms. And when you do that, and for that, of course, we have to assume what is the in the x direction, what is the function. Let us assume that that is something like a cost function. So it is something like a, sort of maximum at the middle, and then goes to zero at both sides. So something like that. So this is a very simple x function. So fx is known. Then so it is something like this. Symmetric function will look like this. So it is a localized. It has a scale, and it is maximum at the equator and decreases away from the equator symmetrically, and also decreases from the center to the boundary. So this is the kind of symmetric heating that we are talking about. So with that, if we go, there are only the equations, the coefficients. Only these Q0 and Q2 will remain. Okay. And then all the other coefficients will be non-zero coefficients will be Q0 and Q2, and they will be governed by these two equations. And then this equation, suppose in the absence of this forcing, this equation is very simple, right? It's a kind of decaying functions. And this is also a decaying functions, but it is decaying at the rate of 1/3 than this function. So that in the absence of any forcing, suppose I just put, so this equation essentially, so this is essentially associated with the Kelvin wave response, and this essentially is associated with the Rossby wave response. And this structure will also tell us that. So we can actually now put in the solve these for cos x function. We can solve these now. So we can find the inhomogeneous solution. Over the region of forcing, there will be the forced inhomogeneous solution, but away from the forced region, the solution will propagate as a free wave, right? So at the boundary, we have to sort of match them, and if we do that, you will get the exact solutions as a function of space in the x as well as in the y direction. So this looks complicated, but it's not a big deal. It is a solution of these equations only, and matching the boundary conditions, the free solutions and the forced solution at the boundary. So that gives us the solution, and once these solutions are there, then you can plot, and then from there, of course, once I have these Q0s, I can have the U's and W. V is of course 0 for the first one. The V is 0, and this essentially gives me a sort of a Walker circulation in this. In this, I'll just tell you that. So, but the second part represents the n equal to 1 Rossby wave solution, and that is essentially a planetary wave propagating westward. And these solutions, now I can plot these solutions in this form. Together I can sum them up and plot, and this the Q0 solution plus Q1 Q2 solutions, if I plot, this looks like that. So essentially it is very similar to, remember, this solution is very much similar to what we found in the Matsuno's that periodic solution, but now it is localized because it is it has to be, because this is very symmetric, like exactly what Matsuno had taken, this is a, Matsuno had one more here, periodic solution. So now instead of that, now I have this. And so the localized, and this response has to come from the Kelvin wave response and the Rossby wave response, and that essentially gives me a structure similar to that. And this structure has this is the heat source over here, symmetric heating, localized heating. It will produce vertical velocity. This is actually vertical velocity plotted here. So a sort of implied vertical velocity, because if it is shallow water equation, we don't have any vertical velocity. But since we have assumed a vertical structure, we can talk about a vertical velocity. And that is, and this is the implied vertical velocity, ascending motion here, descending motion here. So this is a kind of, so ascending motion here and descending motion on this side. So this is what is known as the Walker circulation. So over the region of heating, there will be ascending motion, and then the descending motion to the east is much wider because of the fast propagating Kelvin waves, which will then take the signal much farther before getting dissipated. On the other hand, on the western side, the circulation is actually limited, because the Rossby waves, as they propagate slower, 3 times slower, they get dissipated at a distance much closer to the source than the on the eastern side. So this is consistent. In fact, it turns out that the Walker circulation in the atmosphere has similar asymmetries like these, similar asymmetries like that, and that is the beauty of this analysis and this work of Gill. And that, of course, this response we have already discussed, that the Rossby wave response will have this twin vortex on the western side, and that is V is antisymmetric, U is symmetric. See, the U winds are very much on both sides of the equator. They are similar, identical, but the V winds are opposite. So that is the structure. So we can do that. The point is that that given this a localized heating also, I can analytically solve, and that is the beauty. So now let us look at a antisymmetric heating, which is like this, where this is, instead of e to the power minus y square by 4, it is y into e to the power minus y square by 4. Now, when you go to the put them into the system now, into the equations, then the non-zero coefficients, Q1 has a non-zero coefficient for n equal to 1, and therefore Q1 is equal to fx. So that Q1 is fx, and then here there will be Q1, which is the small Q1, that will be 0, and V0 will be proportional to this. So this is related to a mixed Rossby gravity wave response, and that we'll see in a minute. So this is this again, we can do the same thing we can do now, only some of the coefficient equations will be different. Now these coefficients, Q1 is equal to 0, V0 is equal to Q1, that we have found, but now we have an equation for V2 that Q3 will remain, and Q1 is 0, but only Q3 will remain. Okay, so these equation we have to solve, and that will give me solutions for V. V is so this U, V, and phi. Now I can, having obtained these are of course a relationship that comes from the basic equation. Now once I plot the solutions, the coefficient, find out what is the Q3, what is the special structure, and V0 is given by Q1, and with that, So this part essentially Q0 is equal to 0 and V0 is equal to Q1 represents a mixed Rossby gravity waves. And this is because the Rossby gravity wave is kind of stationary, because it is very long wave Rossby gravity wave. As I mentioned, it is not producing eastward response. And it also does not go in the westward direction. Also, it does not go beyond the forcing region, because it is more or less stationary. Because the K is very long waves, the frequency of this Rossby wave is 0 nearly, and that is why. And both sides, even if it is slightly not exactly 0, on either side, if there will be the eastward propagating, westward propagating, both of them will give rise to stationary structure. And that is why this response is stationary. So only response that we get is from this n equal to 2 planetary wave response, and that will give me these the other things. And that when you combine these two, we get a response as something like this. So here there is no response to the eastward side at all. From the forcing side, it cannot produce a Kelvin wave response. On the other side, it produces a Rossby wave response which can propagate westward and produce these winds. So it has, interestingly, because antisymmetric nature, the positive heating to the north and negative heating to the south, produces a cross equatorial flow. It is something similar to what we get in the monsoon. So monsoon is actually a antisymmetric heating, not exactly antisymmetric, but of equatorial heating. Now I'll come back to that in a minute, where if I combine a antisymmetric heating and a symmetric heating, then what will happen is that symmetric part of this on this side will be added up, and the other side it will be weakened. So it will essentially become an asymmetric of equatorial heating. So a combination of these two can give me a monsoon-like heating, and that is what is very interesting about these. So this is what, if we add now these two solutions, I can get a monsoon-like heating. And this is, look at this the cross equatorial flow. So there is a heat source here, and this cross equatorial flow turning around and producing cyclonic vorticity, low level wind. Only thing is that we are not getting something like a westerly jet that we observed. So that reason for the westerly jet is slightly different, and I will discuss about that when we discuss the monsoon. But the fundamental the wind structure associated with the monsoon can be explained very much like from this kind of a very simple response to the heating, response of the atmosphere to heating associated with these precipitation and convection. So this is so in conclusion, the interpretation of the equatorial part of flow in the lower troposphere with a very simple analytical model. The Walker circulation is driven by the response of the symmetric heating. Hadley circulation is driven largely by the antisymmetric heating, and the solutions were found for only one mode. Solutions for semi-infinite atmosphere can be found suppressing superposing different solutions. So more complicated heat source. Now that we know that these solutions can be found for symmetric, antisymmetric, I can have now more complicated heat source, and then for them also we can. It all depends on how your heating is projected into which kind of normal mode it gets projected into, and for that normal mode the response will be generated, and that is what gives us a framework for understanding even a much more complicated response, a much more complicated heating function. So there are some important issues here that I would like to comment before concluding. So you see that here we are getting this response. We assume a heating or epsilon, this Newton relay friction. This in a non-dimensional sense, it actually represents about time scale of about 2.5 days. This value is to get the right kind of wind, sort of approximate wind strength. You need these and the structure. You need these this. But where does this come from? In the free atmosphere, this kind of dissipation is not there. So, but we are talking about if atmospheric actually. Not we are not talking about boundary layers circulation. We are talking about the atmospheric circulation, which is in the free atmosphere. Where so there is a bit of a problem here. So before that, let me talk about one thing. So now this structure of the large scale structure of the wind very much depends on what kind of dissipation you use, because as I said, the dissipation will make. If the dissipation rate is high, then this will be restricted to a smaller region. If dissipation rate is low, the whole response will be over a larger region, broader region. So dissipation rate is important. Now that is where this question comes in. So if suppose so this is question I have I assume that so this if the dissipation rate were small in the free atmosphere, then the structure will be different and the structure will be larger. And so what is the rationale of using this? So this rationale is so it's actually you can think about this response as actually as a lower level atmospheric. One way of looking at it is that it is like a boundary layer response, and so it depends on how you use this and to add that about actually free atmosphere, you have to add another layer where you have a different different dissipation and combine these two. And so therefore there are issues like that. So some of the issues that we need to discuss. Also remember, I have few comments on these, but so I'll give you one or a couple of examples of how these Gill models has been applied to some. In fact, one of my students actually combined this Gill model as well as this boundary layer. There are other boundary layer models, boundary of surface winds. When we talk about surface winds, we have to add more different physics also, because surface winds can be affected by not only the heating forcing in the upper atmosphere, the heating from the free atmosphere, but also it can be affected by sea surface temperature gradients. That is what the Linzen and Nigam, they did a study where the sea surface temperature gradients in the ocean itself can give rise to pressure gradients. These pressure gradients can give rise to the low level winds. So the near surface winds can be affected by sea surface temperature gradients, as well as also forced by upper level sort of pre-atmospheric heating above the boundary layer will also force winds at the boundary layer. So these two things have to be combined, and we did a simple study some time back to actually show that. It's the Gill, the ENSO response I mentioned earlier, that so many of these response of the ocean to the winds producing and oh, I'm sorry. So this is actually something else, but unrelated. some so this so now this response of the sea surface temperature to the so we have given a prescribed heating, but how do we link it to the sea surface temperature? So so that for some of the couple model, when you develop a couple model, then I want the heating in the atmosphere to be linked to the sea surface temperature, and then and that sea surface temperature will give rise to heating. Heating will give winds. The winds will then force the ocean. Ocean will then go and produce a change in the temperature. Temperature changes will further change the heating function, and that will they will couple. And so people actually took this model and then made the heating proportional to sea surface temperatures and anomalies, and then use the model which is response of the to study the response of the atmosphere with changing sea surface temperatures, and that kind of a model has been used to study the response of the wind anomalies. This is Zebiak had done a lot of work on this in the many years ago, and that model went to form a sort of Ken-Zebiak model, and there they studied the associated with sea surface temperature anomalies, how the wind response will be generated as a function of the sea surface temperature anomalies. There are some issues, but this is how we can sort of build the basis for developing simple coupled ocean atmosphere model. With that, I think I'll stop here.